Okay, perfect. So, welcome to Physics 7. So, I'm Cerise and I'll be teaching today. Just a reminder, I think you get this at the beginning of every class, but this is run through MCAT 101. We're a nonprofit in the Commonwealth of Virginia. And basically, we're here to help you in several methods of communication. So, you can always contact us through Slack or email. The session is being recorded. Um, so you'll be able to access not only the recording but also the slides. So don't worry if you want to take notes. And also, if we don't have time to get through all of the content, the full slide deck will be available to you. So you should be able to go back and look at the slides that we didn't get a chance to get to. Um, Yep, you can always email us at info@premedpeers.org, or you can reach us through Slack. So kind of the typical things. So we will go through some homework questions today from Khan Academy, and then a few varsity tutors and my own written question, and then some content review, and finally we'll end with a practice passage. So today's content covers lights, mirrors, lenses in quantum physics, but mostly heavy on like light, so reflection, refraction, and then mirrors and lenses. So if there's anything on this list that sticks out to you as something that you might want me to spend a bit more time on or make sure that I get to, feel free to drop it in the chat. I have slides prepared on everything, or everything listed here. So hopefully we'll just have time to get through it all. But if you notice halfway through that we haven't gotten to like vision correction yet and you'd really like me to go over it, like feel free to just drop it in the chat and I will just skip ahead. So happy to take questions and suggestions as we go along because I want this to be as helpful for you as possible. And we only have a short hour. Okay, so with that said, if anybody has a specific question from the homework, I think homework was pretty long for this week because it was several sections on Khan Academy. So I've only picked like 3 or 4. But if you have a specific question, you can always drop it in the chat, or also you could just message me on Slack or send it in the large group and just say like, whoever was teaching tonight, if you could, help me with this question, just let me know because I know there was quite a few and they're quite a variety of topics. So the first question that will go over is, oh, it's missing the actual question. It's basically, the question is, what is the distinction between like light and sound waves? Like which comparison between light and sound waves is accurate? So if you have ideas, you can drop them in the chat. And if you're willing to explain an answer ever, like if you drop an answer and you want to explain it, you can add a star next to your answer and I can call on you, but otherwise I won't call on anyone. Okay, any last chance? So kind of the appropriate comparison for this question is that, oh, this is actually, okay, I'm going to skip this question and fix it. It should actually be D. I think it got moved when I edited the slide. That light waves can be polarized while sound waves cannot be polarized, and that comes from basically because light waves are transverse, so they move into basically 2 dimensions, and I'll have a good picture of this later. So oscillations are perpendicular to propagation and are always transverse, which means that basically you have and I'll show you the picture, basically you have it moving in 2 dimensions versus sound waves, the oscillations are parallel to propagation. So the wave oscillates in the direction that the wave is actually traveling. And I'll show you a picture later. Okay, so this question is, what is the height of an image of an apple? sitting 2 meters away that is projected onto your retina if the focal length of the retina is 20 millimeters? Anybody have any ideas? Please don't be afraid to put answers. I don't know. I know there's quite a few questions in homework, so okay, so the answer for this one is D, 0.12 centimeters. And so here I've just written out the answer for you by hand. So we know that magnification is I over O, meaning image distance over object distance. And that proportion should be the same as the height of the image, which is 12 centimeters over the height of interest, basically, um, which is which is 12 over h, which is then equal to minus 200 centimeters over 2 centimeters. So basically, we have the actual image of or the actual height of the object, excuse me, which is 12 centimeters. We'll divide that by the image height of h. That ratio should be the same as the object distance, which is 2 meters, so 200 centimeters, divided by 2 centimeters for 20 millimeters. So it's 0.12. Okay, so the next one is, what would the critical angle be for a flare lit underneath the surface ocean if the index of refraction for ocean water is 1.33? Any ideas? Oh, any ideas? Okay, so this is asking for the critical angle. So to find the critical angle, we can use this formula, which is that sine of the critical angle equals n2 over n1. So we are starting in water and we are going into air. So in this case, N1 would be the index of refraction of ocean water, and N2 would be the index of refraction of air. So we get 1 over 1.33, which is inverse sine of 3/4. So I just wanted to give a bit of background. I personally have found critical angles, I found them confusing when I first learned them. So one thing that helps me to remember kind of how we get this equation from like sine theta c equals n2 over n1, it's basically because when we're at when we are at the situation where we are at like the critical angle, that means that theta 2 is equal to 90. So sine of 90 is 1. So this equation simplifies to n1 sine theta 1 is equal to n2. So then you just solve, you would get sine of theta 2 equals n2 over n1, and then you take the inverse sine of that. So because we're looking specifically for the critical angle, I think that math kind of helps you show how you get to this equation. So you can obviously also just memorize it, but for me, it helps to know where it comes from. Okay, so then the last question is, which of the following statements accurately describes the sign conventions used for the thin lens equation? So any ideas? Okay, so this is true. So the magnitude of the magnification indicates whether an image is enlarged or reduced, and the sign indicates whether it is inverted or upright. So that is true. So one thing to note here is that C is could be the case. C could be the case, but it actually depends on where your light source is located. So I'll cover this a bit more later. Um, but like to the right of the lens and to the left of the lens is not how these signs are defined. They're defined as what is on the same side of the lens as the light source. So C could be true, but is not really specific enough, and we would need more information. And D is also not true because, um, again, it would be helpful to know what side of the light source, like what side the light source is on. But also typically, if an image is formed on the same side of the lens as the light source, then it would actually be negative. So if you found yourself considering either of those, that's why they would be wrong. Okay, so I have a few quick warm-up questions. So the first is, what color of visible light contains enough energy to eject an electron off of a metal with a work function of 3 electron volts? And it's a bit of math, but even if you can just kind of set it up, I'll give you like 1 minute to try and set it up. Okay. So this question has a few steps, but I think it's a good example of, oh, perfect. Thank you. Yeah, so C is right. So C being violet is correct. So basically, the way you have a few steps. So first, the assumption that you're working with is that you need the energy of your photon to be basically greater than or equal to 3 electron volts, right? Because that is the work function of your metal. So you must exceed that in order to get any electrons to be ejected. So we have this equation that E of a photon is equal to HF. H is given to us, which is nice. And we also can kind of extend that a bit further, and we know that that's Hc over lambda is 3 electron volts, and we're also given C. So now this is looking pretty nice because we know H, we know C, so now we just need to figure out lambda. So from there, it's just a bit of math. So you can convert electron volts into joules, which is, again, that conversion is given for you. It's kind of a hint. So once you convert into joules, you basically then just set up for solving for lambda, and you should get about 415 nanometers, which is on, uh, I mean, this is lower, oh, it's lower wavelength, so higher energy. So you know that that should be like on the violet spectrum, violet end of the visible spectrum. Any questions on that? Okay, so another photoelectric effect question. So in the photoelectric effect experiment, incoming photons with enough energy cause the ejection of an electron from the metal plate, proving that light carries energy. What color visible light would you expect to produce the fastest ejected electrons? Any thoughts? Oh, so interesting. So we have a couple answers, and you've actually picked opposite ends, which is interesting. So somebody said blue, and blue is correct. Um, so I think this is a good conceptual question that reminds you of a few different pieces. So again, we remember that the energy of the photon is hf. So the photoelectric effect is basically, you're taking the light from the photon And then when you eject an electron off, that electron basically has kinetic energy equal to the energy of the photon or equal to the energy of the photon minus the work function of the metal. So the energy of the photon will be basically transformed into kinetic energy of the ejected electrons. So photons with higher frequency, based on this equation, would have more energy. So higher frequency would mean lower wavelength, right? So you would expect the color with the lowest wavelength to cause the fastest ejected electrons. So kind of similar concepts to, oh, good, I'm glad that makes sense. So kind of similar to the last question, but more conceptual way to test it, which is kind of nice because obviously the math in the last question, good to practice, but it's quite a bit of math for like a multiple choice. So um, I think that this is kind of a good way to test your conceptual understanding. Oh, oh, sorry, I messed up and I circled it already. I had a good diagram for it. So light passed through a series of two ideal plane polarizers at an angle of what would result in 0% of light being transmitted. So unfortunately, I have circled it, but the answer is 90 degrees. But I've drawn out here why that is the case. So I think this is again kind of a conceptual question for what actual like what plane polarization means for light, and also like seeing that light travels kind of, it oscillates perpendicular to its direction of travel, right? So at the top here, you have like an EM wave, and so you have an electric field in one direction and a magnetic field in another. So if it's passed through a polarizer that polarizes in the like vertical direction, right? Kind of like I guess you could call it the y-axis, you lose essentially that blue piece of the wave. So you're left with the purple. So then you now have like a wave that exists in one dimension. And so if you pass it through another polarizer at a 90-degree angle, you will lose almost like that purple piece of the wave and you end up with nothing. So this is kind of a classic polarizer question. And again, I think a good one to test if you actually understand what it means that light oscillates perpendicular to the direction of propagation. Are there any questions on that? Okay, so I'm going to head on to content then. I'll give you guys a chance now. If you have anything from that first slide that you would like for me to skip ahead to, just let me know. Otherwise, I will just start from the beginning. So this is a little bit what we just talked about, but we'll start with just electromagnetic radiation. So the electromagnetic spectrum goes from radio waves to gamma rays. So in order of increasing energy, you have radio waves, then microwaves, then you have IR, you have visible light, and remember you go from red to purple, so 700 to 400 nanometers. And then after that, you have ultraviolet, X-rays, and then gamma rays. So we talked about this already, but electromagnetic waves are transverse waves. So that means they oscillate perpendicular to the direction of propagation. So in this case, you would have the direction of propagation is along this axis. So you have oscillation in the other two dimensions, basically. It's important to know that visible light is between 700, like roughly 700 to 400 nanometers, and knowing that that goes from red to purple. And then another important kind of just like number to remember is that the speed of light in a vacuum is 3 times 10 to the 8th meters per second. So polarization, so unpolarized light, which is kind of like the light that you would get from a light bulb, has a random orientation of its electric field vectors. So plane polarized light is light where all of the electric fields of the waves are oriented in the same direction. So you can take light from something like a light bulb, right? And you can pass it through a plane polarizer, and you end up with light that's all like a wave that's all oriented in the same direction or kind of like on the same plane, right? Which you could guess from the name being plane polarized light. Okay. So then that kind of brings us to how we can manipulate light. So there's reflection and refraction, and obviously they sound similar and can be easy to mix up. But reflection is the rebounding of incident light waves at the boundary of a medium. So this is another thing that you've probably seen before is that light waves that are reflected are not absorbed, right? So what you see, like when you look at a green plant, right, you're seeing the green light that is being reflected. So that is actually everything else is being absorbed, right? And you see what's being reflected. And then there's refraction, which is the bending of light when it passes from one medium to another. So basically the bending of light comes from light changing speed as it changes a medium. So light slows down when it goes through a medium with a higher index of refraction. So I like to think of index of refraction almost as like, opposing the movement of the light through it. So light slows down a bit. So there's an equation for this. So the typical equation, its normal form is n equals c over v. So again, c being um, the speed of light in a vacuum, and then v being its speed in the medium, and then n is the index of refraction. But if you rearrange this to v equals c over n, you can quite easily see that v would get smaller when n is greater than 1, right? So as you increase the index of refraction, you slow down light. Okay. So there's one kind of key law I'm guessing you've seen a lot. Snell's law describes refraction and how light bends. So the equation is at the top here. So n1 sine theta 1 equals n2 sine theta 2. So basically, when light enters a medium with a higher index of refraction, it bends towards the normal. So in this picture, right, you have like, say this is just a boundary between a medium of n equals 1 and n equals 2. Your normal forms like a 90-degree angle with that boundary line. So you have this incident angle. And so you would have this angle would be theta 1, and then this angle is theta 2, and you can see that as it enters the medium with a higher index of refraction, it bends towards the normal, and that angle between, its path and the normal gets smaller because you're increasing n2. So sine of theta 2 must go down. This is where remembering your unit circle can also be helpful because it's good to know that as theta increases, right, sine increases. So that comes from, you can think of the unit circle, right, that sine of 90 is 1. So it's good to remember that relationship because it helps me kind of intuitively understand this picture. So the opposite happens when you go from a medium of higher index of refraction to one of lower index of refraction, your ray would bend away from the normal. Are there any questions on that or any of the slides so far? Tell me if I go too fast. Okay, so this brings us to total internal reflection. So I talked a bit about this before, right? But basically, you have Snell's law, and so for me, it's helpful to think of total internal reflection as kind of just a special case of Snell's law. So remember earlier, I drew a little line through this, and I said, well, sine of theta 2, because we're basically saying that this ray represents the critical angle, right? So the angle between this ray and the normal is 90 degrees. So that would mean that theta 2 is equal to 90. And essentially, it can't exceed 90. So rather than kind of going, down here, which would be greater than 90 degrees from this normal, it what happens is total internal reflection. So no longer do you get refraction, you get reflection. So once theta exceeds the critical angle, that's when you get total internal reflection. And so that's what's written here, right? And then, if you simplify this, so if you set this equal to 1, you would get n1 sine theta 1 equals n2. And so then you just rearrange and you can designate that as your critical angle. So sine of your critical angle is n2 over n1. Does that make sense? Also good, okay. Also, if you ever I mean, I know I'm going quite quickly, so if it seems like it's making sense now, but when you're looking back at the slide, something is unclear, just let me know, because I think sometimes it's easy to hear it and kinda think it makes sense, and then you look back at the slides and you're like, "I don't know what she was saying," so just let me know if that happens later on, I'm happy to answer questions later. Okay, so that's kind of reflection and refraction. So then we have diffraction and dispersion. So I'll cover these quickly because they're kind of they're a bit more equation based. So dispersion is basically when wavelengths of light separate from each other. So, the classic example that's given is when you send white light through a prism and you get a rainbow, right? So, you separate out the different colors of the light that all would usually combine to create white light. That's dispersion. Diffraction is how light spreads when it passes through a narrow opening. So you have single slit diffraction and double slit diffraction. So n being the number of the fringe, and then a being the width of your slit. And then for d, you would have two slits, and so they're d distance apart. And then n plus one half lambda. And I can go back in and add pictures for those as well, because I think that that might be helpful. But these are just kind of the equations that represent single and double slit diffraction. I believe n is the number of the fringe. So basically, when you send light, I'll look up a picture and add it. But basically, when you send light through a single slit, it spreads out, right? So you get like like a light, meaning literally lighter, like it appears lighter when you view it. You get a light fringe and then a dark fringe. So you get a pattern of the light. And so n, I believe, is the number of the fringe. But I will add that to the slide after this so that it's more clear. Does that sound good? Okay. So then we're kind of moving into optics. So some general rules for optics, which are true for mirrors and lenses, and that I think are just good to have in the back of your mind. So, an image is real if light actually converges at the point of the image. So, for example, if you think about like somebody who wears glasses, right? Um, if there is a light shining like towards their eyes, right? That would be the normal case. And there's an object between that light and their glasses. That's your object, right? Um, so basically, light hits that object, and then um, like light comes out, and then it goes into your lens, and then that light converges behind the lens of your eye on your retina, and that's where the image is made. So an image in that case that's made on your retina would be real, right? It's made on the opposite side of the light source as the object. And it's the opposite for well, it's not the opposite for mirrors, but it's different for mirrors because if you think about standing in front of a mirror, um, the light would hit the mirror and then it reflects back, right? So light would hit the mirror and then actually travel backwards. And so a real image for a mirror is made in front of the mirror. Does that make sense? So then the opposite is true for, or like images are virtual if light doesn't actually converge at the point of the image, but only appears to be converging there. Any questions on that? And I'll cover it again with a bit more detail on the slides. Okay, so some kind of information for mirrors. So concave mirrors are converging, which means that they have a positive focal length. So it can be difficult to keep mirrors and lenses straight. So I would remember primarily that a converging system has a positive focal length and a diverging system has a negative focal length. That is true of mirrors and lenses. What changes is that a concave mirror is converging, and at the for a lens, it'd be the opposite. So a convex lens is converging, and this will be on both of the slides. Um, so yeah, so concave mirrors converging, positive focal length, and then convex diverging, negative. And then this is what I was kind of just describing. So basically, for a mirror, if you have an object in front of the mirror, meaning on the same side of as a light source, that's typically what I mean by in front of, that has a positive object distance. And that would make sense, right? If you're standing in front of your mirror in the bathroom, you want light behind you so that you can actually like get anything to kind of enter the mirror, right? If it's dark, then nothing would happen. So then an image made in front of the mirror is a positive image distance, and that would be a real image because the light would hit the mirror and reflect out. One equation to be aware of for mirrors is the focal length is the radius of curvature divided by 2. Is that all making sense so far? Any questions? Okay, I'm going to keep going. So lenses, I just said this, right? So convex lenses are converging. Again, converging systems have a positive focal length. So that stays the same between mirrors and lenses. Concave lenses are diverging, they have a negative focal length. So an object on the same side of the lens as a light source is a positive object distance. That makes sense. If you are, yeah, if you're wearing glasses and you're looking into a room, you have like ambient light. And if you want to look at something, it would be in the light, like on the same side of your lens as the light. Um, but then an image for a lens that's formed opposite side of the lens as the light source, that's a positive image distance, and that is a real image. And then an image formed on the same side of the lens as the light source is a negative image, and that would be a negative image distance, and that would mean that it's a virtual image. And that's because remember that real means that's where the light rays actually converge, right? So if you have a lens and you pass light through it, the light rays will actually converge behind the lens, essentially, or on the opposite side as where they started. Because they pass through the lens, they bend. Can I give an example? I think the examples will be in the questions. What do you mean by an example of the last two? Or like like an example question? Because we'll do some. And then if that doesn't help, just let me know. Okay, I think the figure in the practice passage will be helpful for that. But if it's not, just let me know and I can find you a new one. Okay. So then I've put here just one quick um, equation for lenses in series. So if you have multiple lenses, then basically their powers will add. So power is 1 over f, and that'll be on a slide, but the powers just add like this. Okay, so important equations for lenses. So like I just said, power is 1 over f. So power is in diopters and your focal length is in meters. And we'll see this in the practice passage. But this is important to remember. If you're given a question about power, it's a very easy way to trick you because if they give you a focal length in millimeters, for example, you have to remember to convert it to meters. Otherwise, you'll get a wacky number. And then the sign conventions that I just talked about, hopefully they are clear by now. If they're not, just let me know. But the sign conventions for object and image distance, you may have wondered why I cared so much about them. It's because they influence this equation. So this is kind of like your most important, thin lens equation. So it relates the image distance, the object distance, and the focal length. And then this is where your sign conventions matter. So if you know you're forming a virtual image, for example, that would have a negative image distance, then you would have to make sure that you flip this sign to a minus when you're working with this equation. magnification is equal to the negative image distance over the object distance. So remember, we talked about the magnitude of this result gives you an idea of the size, the height, whether it's enlarged or shrunk, but the sign tells you whether it's upright or inverted. So there's kind of two pieces to it. Okay. So one last thing for lenses is vision correction. So you are expected to know that myopia is nearsightedness. So that means that you can't see things far away easily, right? So I have myopia, so I can see my phone very well, but if I look up to look at the TV or something, I struggle to read it. So that means that you would need diverging lenses. And then hyperopia is the opposite. So that's farsightedness, meaning you can see things far away well, but not things close up. And then you need converging lenses. So one way that I just thought of earlier to remember this, you could think that for nearsightedness, you need lenses with a negative focal length. So you need diverging ones, which would be negative focal length. So that could be a way to keep nearsightedness straight with what type of lens that you need. And then obviously, in that case, you would just have to remember that farsighted would be the opposite. So nearsighted, negative, diverging lenses. And okay. Um, any questions before we go on? And we'll do a practice passage on optics. So we'll get a chance to practice that a bit. Okay, so the last thing is the photoelectric effect, which we did a couple of questions on already. But basically, when light with a high enough frequency hits a metal, the metal will emit electrons. And so when I say with a high enough frequency, I mean with basically sufficient energy to overcome a work function that the metal has. And then remember that current is just flow of charge. So if you pop electrons off of a metal, then that produces a current. So I have here the two big equations. So E, this is E of a photon, equals hf. H is Planck's constant, F being the frequency. And then you're often can be asked for the kinetic energy of an electron, or you could be asked for how fast it's going, in which case kinetic energy is equal to 1/2 mv squared, right? So you can very easily get from kinetic energy to velocity, but that is equal to hf minus the work function. So basically, you shoot a photon at a metal, it has some sort of energy. Some of it is basically lost to the metal, and that's your work function. So when you're thinking of how much energy basically ends up in the electron, you have to take out the work function. Um, one thing that I think I wanted to kind of harp to get straight is there's kind of one key distinction to remember. So the energy of a photon increases with increasing frequency. So we can see that from this equation. That translates into higher kinetic energy of the emitted electrons, which means that they move with higher velocity. Okay. But you can also be asked questions about current, and I think that can get confusing. So I've clarified it here a bit. So the number of emitted electrons increases with the number of incident photons above the threshold energy, and so that leads to higher current. So if you're worried about the velocity of your emitted electrons, then you would be worried about the energy of the photon. But if you're worried about the current that's being produced, then you care about how many photons are hitting your metal because you care about how many electrons you're getting to pop off. Okay. Any questions on the photoelectric effect? Incident refers to high enough energy photons. So, yeah, this is a good question, and thanks for asking. So, an incident photon would just be any photon that hits the metal. So that's why I said here I kind of caught myself. So, um, when I say that the number of emitted electrons increases with the number of photons, those photons have to be above the threshold energy. Because in theory, if you think back to that first example we did, if your metal has a work function of 2 electron volts, for example, and none of your photons have 2 electron volts of energy, then no electrons will be popped off. So you would have no current. So you could hit that metal with like tons of 2 electron volt photons, but you still wouldn't get a current. But if you hit it with a lot of 4 electron volt photons, then you would get more current. So that's what I mean by like number of incident photons above the threshold energy, meaning like the work function energy. Yeah, thank you for asking. Okay, so I have kind of a short passage. So let me see if I can. Oh, so I have the passage here, but I can also send the link in chat. Let me just pull it up. I'll leave it up for your reading now, and I'll grab it and drop it in the chat too in just a second. Okay, so this is the link to the passage, which will have the questions, put next to the passage. So I will give you all, let's say let's say 7 minutes to read and get through as many questions as you can. And then I'll also give us like 30 seconds when we're going through the questions to give you a second chance at them. Okay, so we'll reconvene at 6:50 Eastern. Okay, so hopefully you had a chance to get through most of the questions through Jack Weston. Okay, so let's just get into it. So the first question is on the left-hand side of the optical bench, where could a research team place an object and create a virtual image? Um, so remember that for a virtual image, that would be a negative image distance. So that would be um, the image forming on the same side of the lens as the light source and the object. So any ideas for this one? Nope. So for this one, it's B. So I think this graphic is actually quite helpful. So if you kind of take this almost as its own little picture, I've added in these little abbreviations. So essentially, this if C is the focal point, which you can gather from the passage because it tells you that each of the distance between each of these dots has to be 10 centimeters, and it tells you the focal length is 20 centimeters. So we know that if we put something at C, that would be at the focal length, right? So there's a nice little mnemonic for this. So if you're at the focal length, you do not form an image. And I'll add that to the slides. I didn't add that to the slides yet. So if you're at the focal length, you don't form an image. If you're within the focal length, you form an upright and virtual image. And that's because the light rays will not actually, um, it's because of like if you draw a ray diagram, the light rays would not converge back here, that you would have to reflect them out and they would converge here. So when you're inside of the focal length or closer than the focal length, you form an upright and virtual image. And if you're outside of the focal length, you form an inverted and a real image, and that's because the light rays will pass through and they will converge on the other side. Um, and so I think that this is a good visual of kind of how to remember that. So no means no image formed there. So I remember it as like IR, no UV. So, as you go out from being far away from the lens, inverted and real. When you're at the focal length, no image is formed. And then when you're within the focal length, you have upright and virtual. Does that make sense? And I can also look up those ray diagrams and add them in too. Okay, so if the object is placed at point A, where will the image be located? Any ideas? Okay, so the answer to this one is exactly at I. And I think that might seem like an intuitive answer, but you can also show it through the math. So rather than just eyeballing it, you would want to check it with doing a bit of math. So you can use this thin lens equation. And so this is kind of a good example of why sign convention matters. So we have a convex lens that's given to us in the question. So we have a positive focal length. So our focal length is plus 20 centimeters. So we can plug our numbers in. So we know again that each of these is 10 centimeters. So if we place something at A, um, sorry, I skipped a step here. I just rearranged to get 1 over I equals 1 over F minus 1 over O. So you get 1 over 20 minus 1 over 40, which is the object distance. And then you can move from that to 1 over I equals 1 over 40. If that steps confuse you, if that step confuses you, I've shown the fraction math here. I know when you're working with inverses, they can be a bit tricky to kind of remember how to do the math. So you can simplify it to 2 over 40 minus 1 over 40. So it's 1 over 40. And then I is then equal to 40 centimeters. And remember, that's the image distance. So and then you can think 1, 2, 3, 4, it would form exactly at I. And then that would be an inverted and real image, right? So that's another thing you can kind of check your knowledge as you go and add on a bit more description. So this would be inverted real and formed at I. Okay, so the next one is if a 5 centimeter tall object is placed right side up at location D and it creates an image at point C, what would be the height and orientation of that image? Any ideas? Okay, so it's 10 centimeters and right side up. So remember that magnification is equal to minus I over O. So in this case, um, that is equal then to um, the height of the objects, right? The ratio of the height of the objects, which is equal in turn to the ratio of their distances. So this is the ratio of the height of the object. So I over 5 centimeters, because we're working with a 5 centimeter tall object, is equal to minus the image distance. And in this case, the image distance is minus 20 because we're working on this side of the lens, right? So this is a negative image distance over here. It would be positive if it was over here. So minus negative 20 over 10 centimeters, which is um, the location of the object. So we get I over 5 is equal to 2. So I is equal to 10 centimeters. And then again, I've just made the sign in red here to remind you that that's important. So we ended up with a like implicit plus. So that plus tells us that the image is right side up. Um, and then 10 centimeters is its height. Any questions on that? Okay, I'll keep going because we're running a bit tight on time. So if an object is placed at point B and the convex lens creates a real image of that object, which position could be the location of that real image? Any ideas? Okay, so it could be to the right of point I. So remember we have inverted. So in this case, it doesn't really matter based on the focal length, but I remember IR means inverted and real, right? So if you want a real image, you would want okay, so inverted and real, but also remember that um, it would be formed on the opposite side, right? Because if it's a real image, then it's going to have a positive distance, which means that it should be on the opposite side of the lens as the object. And since the object is over here, we would have it over here. And so I think I wrote that out for you. Yeah. So real images are formed on the opposite side of the lens as the light source, which is basically almost always the object too. So the image should be formed to the right of E. So the only one that matches this is A. Okay, I'll go on to the last question. So what is the lens power of this convex lens in diopters? Okay, so you have A, which is 0.05. Any other takers? So this one is why I pointed out that you have to be careful with your units. I think that the MCAT likes to be tricky with power questions. So remember, we have a focal length of 20 centimeters, right? So when we use this equals 1 over F equation, and I wrote it in caps here, our F has to be in meters. So we're given a focal length in centimeters. So we need to convert that to meters to get power in diopters. So then power is just 1 over zero point 0.2. And then, sorry, this looks like 50, but it's 5D, so 5 diopters. So that gets you C. But if you forget that conversion, then you could be off by a factor of 100, which would lead you to A. So it can be just them being tricky sometimes. So just a reminder to be careful with units. Okay, so that is the end of the passage, and I've already gone in while you guys were testing, and I added in the explanations of the variables for single and double slit diffraction, and I added one picture, and I can add another. They're kind of hard to find good ones that aren't too confusing. But also let me know if you have any questions. You can always email the Pre-Med Peers in email if you have any questions. Or you can reach us on the Slack. So just feel free to reach out there if something isn't making sense when you're looking through the slides, or you'd like to go over something in a bit more detail. Any final questions or comments? And thank you so much for participating. It's really nice having questions and feedback as we're going. It makes it a lot easier for me too. So okay, I'm going to stop recording, and yeah, feel free to reach out, email, Slack, whatever. But yeah.